Hello everybody and welcome back. Today we're gonna be looking at the saving and loading system. Here we have a new button in the menu that's called Save. When we click on it, you can see here that we're attempting to save and we are saving a few things: the player inventory, the player gold, the player HP into the saves folder here. And then we can see here in an inventory we have an inventory full of logs and we also have no gold. So if we go and talk with the merchant, we can sell some logs to the merchant, and then when we open the inventory again, we see here now we have fewer logs and we have the gold that we got from the merchant. And now if we reload, we can come back here and see in our inventory, the logs are back and the gold is back to 0 because we load our previous save state when we reload the scene. So that's what we have for today. Let's look at how that's built. In the editor here, there's not that many changes. We have a new player data script that we've added to the player where we are getting a reference to the many things that we want to save. For now, we have the inventory, the gold, and the HP. Other than that, everything else is happening in the code. So let's look into that. First, we're going to start with the SafeLoad class here. It's a static class. We're going to be using it directly. We could also set it up as a singleton, for example, or we could find other ways of instancing this class. But for now, we're going with using it as a static class. We have here set up our extension for the save files. We're just going to call them .save. We have a path where we are saving our files, which we're using the application.persistent data path, which will give us a path that's viable here on PC and also when we're using it in the Oculus Quest and wherever we want to deploy this. So we get a path to the application here and add the saves directory here. That will be our base path. And then we have a few methods here. First, we have a generic save method that takes a generic object and a key to store it. The key itself will become the file name. So first we create the directory in the path. This will generally succeed. So we're not checking for any edge cases here. If the directory already exists, it will still succeed. But if we were a bit more paranoid, we could add more error checking here. Then we're getting a binary formatter. We are currently saving all the data into binary files. There are other options. If you wish to save to JSON, for example, the serializer there is better. So it may be easier to save a few classes if you are using the JSON serializer instead of the binary serializer. But for now, we're going with binary. Then we are using this using statement to encapsulate the scope and say, while we're in the scope, use this file stream that we're defining here. And when we go out of the scope, dispose of that file stream. We're working with files. It is very important to make sure that you are handling them properly, and that means both figuring out how to open them properly and then closing them when you are not using them anymore. So that's why we are using this using statement here, to make sure that the file is properly closed when we get out of the scope. And then we have here a try-catch statement. In general, I try to avoid try and catch statements because catching an exception generates quite a bit of overhead, which can be really bad for performance. You don't want to be throwing exceptions all the time. With that said, when working directly with the I/O, it's very hard to avoid exceptions, so you better handle them properly. In this instance, we're trying to serialize the object that we pass to the method into this file stream that we created. And then just adding a little bit of debug logging here, just in case. If for whatever reason we are unable to serialize the object or we have any other kind of exception, we simply log it here with an error. Similarly, for the loading method, we have a generic load method here that just gets a key. Then we create whatever object type we were passed and assign it a default value. That way, if the loading fails, we still get a valid object with a default value. The default value tends to be 0 or null or an empty string if it's a string. Then we quickly check if the save file exists. If it doesn't, we log an error and we return the default value. If it does, though, we get a binary formatter again. Then we create a file stream in this scope and we, instead of creating it like we were doing before, we just open it for reading. Again, using the same path, key, and extension that we defined before. And then we try to deserialize that file and cast it into the type of object that we want. Again, this can fail for numerous reasons, so we want to catch any exceptions that come here and properly log them. And if all of this succeeds, Then we log the value here and return the object that we deserialized. For this saveExists method that we've been calling, we simply get the file name from the string and the path that we've selected, and then we check with file.exists if the file exists. We have here a method that we're not using right now, but can be very useful later on, which we are using simply to delete all save files. This can be good for testing, but it's definitely not something that we would want to use in actual production application. That's why I have it here surrounded by this if Unity editor directive. And then this is simply some IO operations to get the directory that we want to delete, and we just recursively delete all the files in that directory, which in this case will be the saves directory. And we have an extra argument here to pass subdirectory if we want to only delete a few elements here. For example, later on, we could have player profiles and then store every profile separately in its own subdirectory. And then we could use this to clear out some profiles, but not others. Then we have here the getBinaryFormatter method. This is what we're using to serialize all the values into the files. And we have this separately here because we're doing a few things here. The regular way is just to get a simple binary formatter. But because of how serialization works, not everything in Unity is serializable. As we've seen before, for example, Unity has a lot of trouble serializing dictionaries, and you cannot simply serialize monobehaviors or scriptable objects just like that. So you need some helpers, and these are called surrogates. So we first instantiate a new surrogate selector, and then in our case, for now, we're using an item object serialization surrogate that we'll look into in a second, but this is what we're using to serialize the items in the inventory. Then we add whichever surrogates we're using into the selector, and then we tell the formatter to use the selector that we've created and return that. This way we now have the item serialization surrogate working inside our binary formatter here. So let's look a bit into that surrogate here. All surrogates need to implement the iSerialization surrogate interface. This has a couple of methods. One is getObjectData and the other is setObjectData. We'll look at them in a bit. But one of the main things that this surrogate is doing that is different from other loading operations is that if you remember from our items, they are scriptable objects. And the main thing that they have is they're just a name and they're used as a reference in many places. But because they're scriptable objects, they cannot be serialized directly. And more importantly, when they're being loaded, they cannot be deserialized properly in a way that Unity recognizes them. Therefore, we're doing a few things. Here you can see we have two helpers. One is an items array and the other is an item dictionary. And then we have a helper boolean here to see if we have initialized everything. We're using them in this setUpItems method. Here, the key is using this resources.findObjects of type all. We're using this to find all the scriptable objects of type item here. This returns an array of items, and then we are using that array of items to build this dictionary here. We're simply saying that the key of the dictionary is going to be the item name, and the value is going to be the scriptable object itself. And then we set initialize to true. In the getObjectData method, this getObjectData method is used when serializing the object and getting it ready to save. So this is part of the save method. In here, we get the object to be serialized and we're casting it into an item object here. And then we have the serialization info variable here. That's what's actually going to be serialized. This is what's going to go into the file. So we're saying in the info, add the value name and set that to the item.name value. So here we're saving the item name into the file. That's all that's happening here. Then in the setObjectData method, this is the one that happens during the load operation. In here, first we check if we have initialized the dictionary from before. If not, we initialize it. Then we get from this information variable here, we get the key of name and we say that it's a string. So we're getting the string from the name key in the info variable here. We cast it as a string and then we set that as a name. And then we're using that name to look up the actual scriptable object here that we set up in the dictionary. This is because we cannot reconstruct the scriptable object on the fly. we actually need to reference existing scriptable objects. At least for the way that we have set up the inventory, we don't want to create new scriptable objects every time we are loading the inventory. We want to use references to the ones that we've already created. So we set the actual object to that scriptable object and then return it. Then we have the player data. This is a Monobehaviour. We're using this as a place to store everything that we want to save and load as needed. Later on, we may use something different for other variables we may want to save that are not really player related. For example, the state of the world could be saved in a separate Monobehaviour. But for now, we're using this. Here on awake, we are adding two methods to some delegates here. These delegates are pretty straightforward. We'll just quickly look at them. We're setting this game events class. This is also a static class. And we are using it to declare a few actions here. These are delegates that are built into the C# implementation here of .NET. And we have 3 of them. We're currently only using 2, but we have the save initiated and load initiated actions here. These are just delegates that we're going to be adding different functions here that we want to run or invoke when we are saving or loading. Whenever the onSave initiated method gets called from the game events, we're going to invoke all the delegates that are attached to the save initiated action here. Similarly, when we call onLoad initiated, we are also going to invoke all the delegates that are attached to this load initiated action. So back to the player data, you can see here that we are attaching this save and this load methods here to the delegates here. So they get called whenever we initiate the save and we initiate the load. And then we're also calling the load method here directly on awake. This is so that whenever we're loading the scene or reloading the scene even, we run the load method as well. Both load and save methods are pretty similar and very straightforward. We just have a debug line here. Then we're calling the save methods for the inventory, the gold and the hit points. They themselves are also straightforward. We're using the SafeLoad static class that we declared from before. We're calling the save methods here. Here we're saving a list of items. This is redundant in this case because the actual type can be inferred from the object that we're passing, but I'm leaving it here because it serves as an annotation to remind myself of what's actually happening here. So we pass the list of items that lives in the inventory state inside of the player inventory, and we are saving that to the name of the player inventory. Similarly, in the save gold method, we are saving the float value of the player gold. We're saving this under the name of the player gold scriptable object. And we do the same for the hit points. As you can see, these two methods are basically the same, just using different variables. We may later want to refactor this into a singular method, but for now, I'm keeping them separate in case we want to diverge later. And that's it for the saving. The saving part is usually straightforward as long as the serialization doesn't fail. It's pretty straightforward. The loading part tends to be more complicated. So we start with a similar method here. We are just adding a debug line here and then calling inventory load gold and load hit points. In here, we're first checking if the save exists. And then if we have a saved inventory, then we try to load that here with the same SafeLoad class. Using the load method, in this case, we do have to specify the type because the save key is just a string. It doesn't tell us what type of object we're expecting. So we need to specify it here. And remember, we're using the same key as before, the player inventory name. And then we're checking if the items here is not null because the default value of a list is null. And the way that we have set up things in the inventory, if we have a null list, it's gonna complain quite a bit and it's gonna fail in a number of ways. So we're only setting up the inventory here if the items list is not null. Otherwise, the item list will be initiated as usual, as if there was no save. And then we have the gold and hit points methods. These are simpler. We again are checking if we have a save, and if we do, we just load the float directly. This works because the default value of the float is 0, so even if we don't have a save or if something fails in the load method, we still get a 0 here. And we do the same for the hit points. In the case of the hit points, we don't want to initialize a player at 0 hit points if something fails, so we're going to be looking into that a little bit later to see what we're doing there to avoid that issue. here we have the game state monobehavior. This is a helper monobehavior that we're using for a number of things. Here we have some scene management code. We are also using the game state here to actually set the game state. This is its main purpose. And now we're using it also to save the game. This is not the best practice. This is clearly violating the single responsibility principle. But in this case, for now, just keeping everything together here, at some point we're going to have to break this up into more relevant classes. But for now, we're adding here a save method that we can hook into so that we can actually trigger the save. And this is what we're going to be using here when we're calling the save method. We didn't see that before, but this is another change. We're in the in-game UI. If you remember, we now have a save button here. And if we go into the save button, we can see here that we're relying on the game state method here and then the game state class here. And we're calling the save game method when we click on the button. So that's this method. And this method only triggers here the onSave initiated event. As we saw before, the onSave initiated method here calls all the delegates attached to this action. So that's what we're doing there. By triggering this, anything that is hooked up to the save initiated action will get invoked. And that includes the save method here. So that's how we're hooking up the save behavior. One thing that we're missing here is how we're handling the player hit points. As I mentioned before, there can be a number of errors in the input-output library that could lead us to a place where we have loaded something that's invalid and we end up with the hit points being 0, which is obviously not great, since that would basically mean that the player is dead. And I haven't tested out to see exactly what happens if we try to initialize the player at 0 hit points, but we wouldn't want that to happen anyway. So for that particular case, we're checking here now if the current hit points, which are the ones that are going to get loaded, are greater than 0. So as long as we have 1 hit point left, we're going to set that to the current hit points in the damageable object instance. And that's what's actually going to be interacted with all the damageables, and that's what registers the damage when you get hit by the enemy and all of that. So we're setting the hit points at the start here, as long as we have something loaded. If for whatever reason we ended up loading nothing and we end up with a 0 value for the current hit points, then we skip all of these, and then in the damageable object we'll just start at the base hit points, which is going to be 100 in the case of the player. And that is all that we have for the code. It's a pretty convoluted system, but it's also very powerful and it allows us to save and load all kind of objects as we need. For now we're only saving some very simple variables, but we can later tune this to actually save and load different kind of prefabs. And for example, before we've seen using the mesh scatterer, we can end up with big forests and we'll be able to save the actual state of the forest and load it later on to have sort of persistent objects in the world. But we're getting a little bit ahead of ourselves. For now, let's just look at the finished product again now that you know how it's built, and then we'll close for the day. Okay, so here we are again. We can see here as we started that we're trying to load, and we loaded the inventory, we loaded the gold, and we loaded the hit points for the player. So currently 0 gold, 100 hit points, and we cannot see it here, but we have 19 logs here in the inventory. So now let's see this again. We go with the merchant, talk to him, say, hey, I want to sell some items, and select a few to sell. Try to go for 10 of them for 100 gold. Hit the sell button, and now we should have here 100 gold in our inventory, and we have a lot fewer logs. So you can see here also in our inventory is already reflected, and if we go look at the player gold value, it would also be reflected. But the interesting here now is, now if we reload, because we have a previous save, as you remember, we were able to load the inventory and the gold and the hit points. If we reload, everything should be restored, and we can immediately see here that the inventory state now is back to having the 19 logs that we had. And if we open the inventory, we can see them, and we can see that we're back at 0 gold. And even here we can see in the console that we reloaded everything. So that's everything that I have for today. Saving and loading is a particularly difficult challenge because there's so many things that we may want to save, and we need to find a way to properly store that in a serialized format, like we were seeing for a binary format, or if you want to save it in a JSON format. Whatever the case is, you still need to figure out how to represent the data in Unity in a flat file. We may look later into different implementations, for example, for actually saving the position of a prefab here, for example, the NPC for the merchant, or if we want to save the state of the dialogue as we were working before with the dialogue trees. We want to save the quest list and the state of every quest. All of that may require specific surrogates. As we were seeing before, we may need to set up different serialization surrogates for these kind of objects that need specific definition that is not just getting a list of values, but actually may require us to interact with prefabs and with many different operations. So that is a particular challenge with saving and loading, and because of that, I would definitely recommend that you always consider your saving and loading system early on in your projects, because many design decisions that you can make while defining your objects can be later affected by how the saving and loading system works. Just to mention here, the change made here to player damageable, that only came about because I needed to figure out a way to pass in the hit points as saved in the file into the damageable object without having to serialize the damageable object itself. Because if you go into this damageable object instance, it has an actual damageable scriptable object, and that has an internal representation of the hit points that it has. And without this set current hit points method, it would be very difficult to set that up on load. So that is also something that I added here. This is also something that I had to add to make this work. And we didn't look into that initially because it's an ancillary method here that doesn't change much of the functionality of the damageable object. But these kinds of extensions and modifications shouldn't really be happening in later stages. They should come from the design directly. So this is just something that could have been better designed if I was taking into consideration the saving and loading system from the start instead of adding it midway, so to speak. So that's my recommendation for you as well. Consider that from the beginning. Figure out how you're going to save and load your data. If you're going to be using a database or a series of scriptable objects as I'm doing here, or whatever the case is for you, ultimately knowing how you're going to be persisting that data and then loading it back into your game is going to be a more difficult challenge if you don't consider it from the start. But anyway, that is all that I have for today. I hope that it was useful and that you learned something from this. It's saving and loading is hard. So definitely may take a few tries to actually get a feeling for it. But in any case, thank you for sticking around with me, and I will see you again in the next one. Bye for now.